All right, so here is day 2B of Unit 6. And this one is kind of focused because the whole idea is a little difficult to grasp, I think, for some students, for sure, for a lot of students. But I think overall, we don't go too much detail into it. I mean, it's just kind of, we try to do surface level. So if you're in physics, something like this is probably kind of simple for you, but for everyone else, it's definitely going to take some time. Our learning target is I can calculate projections of vectors. And what it is, and actually this arrow here is upside down. This arrow should be going that way, not up, is if this box was on an incline and U is pushing against it, the projection of V onto U, or I should say U onto V, U onto V, and it looks backwards because it's projection U, and then V is the subscript here. That is what part of U is actually pushing the V direction, which if you know the angle of U, you can just find it's like X or Y component depending on which one it is. But if it's at an angle and nothing's really shown here, then I don't really give you the angles of some of these. I just give you the vectors in component form. Then you have to use this formula down here. Okay, so it's the dot product of U and V all over the magnitude of V squared times V. So this right here is going to end up being a scalar, and this is going to be a vector, and when you're done multiplying it, you get a new vector. So if U is pushing like this, that part right there, so this would be the projection of U onto V. So what part of U is actually pushing in V's direction, basically. So let's find the projection of U onto V. And in the easiest cases, when you have both of them in component form, then it's really just a matter of plug and chug, put in the calculator, put in the formula and put in the calculator. So the projection of U onto V for this guy, again, it'd be U dot V. So in this case, U dot V would be 15 plus negative 10 over the magnitude of V squared. So basically just don't square root. Normally the magnitude would be the square root of A squared plus B squared. On this one, instead of square rooting, just do A squared plus B squared. So this would be 25 plus 25, so that'd be 50. And then we're going to take that times vector V. Okay, so on this one, we do know V. We know its magnitude. It does have, it's right 5, down 5, so it has its own magnitude already. And some of the problems coming up, like in example number 2, we don't even have it in component form. All we really know is its direction, and that is enough to do a projection also if you know the direction. So this is a direction and a projection, or I'm sorry, a direction and a magnitude. So they kind of work together. So there's already this force going down. So I guess I should put these on here. So there's this force that's going right 3 up 2, and that's U. And then there's another force that's going right 5 down 5. 1, 2, 3. So part of U will actually go on to V, and it'll be pushed more just because V already has its own magnitude. So here's V. And basically, if I look at this, I want to take the perpendicular down to V. This right here, this little bit, that tiny little mark right there, that's the projection of U onto V. So that's the part of it that's going to be pushing the V direction. So on this guy, this would be 5/50ths or 1/10. So 1/10 of 5. And then I'm going to multiply that out. So it's going to be 1/2 negative 1/2. So that's the projection on of U onto V. Again, I didn't have to know exactly. I could also give you the magnitude of this. We have to know what direction it's going. So this one's a direction and a magnitude, but I could just give you one of those and then in the story tell you the magnitude, so it's not in component form so much. So this guy here, this is where it gets confusing, and this is, I've got Juan is sitting on a sled on the hill, side of a hill. Sorry, it's hard to read. COVID makes your brain a little foggy, I guess. So it's a 45-degree angle. So there's this force pulling down, and 1 is pulling back up. And this is at a 45-degree angle. The combined weight of 1 and the sled is 140. So that's this one right here. That's this F pulling down. So that's 140. What is the force required by Raphael? So Raphael's up here holding it. It's going to hold him up. So how much weight does he have to hold up? It's not going to be 140 because the hill is supporting some of that weight. But basically how much of this is being pulled down this way? Okay, so let's name some stuff here. So here's F pointing straight down. So F would be its force and a magnitude. It's going straight down, so it's going right 0, down 40. So I think of this as 0, negative 140 in component form. So that's the force being pulled down. And then if we look at this, so the way I thought of it is there's this F1. This F1 is being pulled up. That's Raphael. And that's going to be equal to, I just called it V, which is the force going this way. I'm not really sure what it is. So really I'm just going to write it as a unit vector. Okay, so when you get stuck, I really don't know what this is because I don't know what that force is. I'm going to try to figure it out as a unit vector. So think of it, I'll call it vector V. That would be cosine 45. And I'm just going to call it I because I don't know how many I's. We'll just say cosine 45. Again, we're using unit vectors here, plus sine 45j. So I just want to know the direction because I don't know the magnitude yet. That's what I'm trying to find, the magnitude. So I don't really know exactly what it is. So I'm going to just call the direction first. And we'll say that, so F1, which is how much force Raphael is pulling with, would equal the projection of F onto V. Because they're going to be equal because V is pulling down, F1 is going to be equal to that pulling up, so the projection of F onto V is how much Raphael has to pull. Okay, so I guess the way to think of this, we'll say this would be F dot V over the magnitude of V squared. That's going to be a scalar, and I'm going to multiply that by V. Which again, I'm just going to use a unit vector. So if I go cosine 45i, that's radical 2 over 2i plus radical 2 over 2j. You could also just call that radical 2 over 2 comma radical 2 over 2 when you go to dot product form. So the V of this, if I took the magnitude of this, the magnitude is a 1 because I just made it a unit vector. I didn't know how much magnitude it was. I just wanted a direction. So I had to, just so I know it's a 45-degree angle. So it's left radical 2 over 2. Right radical 2 over 2, up radical 2 over 2 is that slope there. So the magnitude is a 1, 1 squared is 1, so it's really just going to be V, or F dot V times V. So the dot product. So if I do the dot product here, I've got 0 times radical 2 over 2, which is 0, plus, and then it'd be negative 140 times radical 2 over 2, which that would be negative 140 radical 2 divided by 2. And I'm going to take that times, again, this is just a direction here now, so the force is going to be in the F1 going down. That's going to tell me my magnitude, what part of that magnitude is going in this direction, going this way. So this is radical 2 over 2, radical 2 over 2. And so this would be, if I add this together, this would be negative 70 radical 2, and I'm going to multiply that out. I'm going to scalar, multiply this scalar in. So negative 70 times radical 2, negative 70 radical 2 times radical 2 would be negative 70 times 2 divided by 2. The 2 is going to cancel out, so it would be negative 70. Whoops. And same thing with the second part. Now they want to know what force, so they're asking for a magnitude. So that just means that if this is pulling down 140, it's actually pulling in this direction, this way and down. So left 70, down 70 is how much force is being pulled. The sled is going left 70, down 70. Now what's the magnitude of that? So squared, add them together, and the magnitude of this guy would be 98.99 pounds. That's awfully close, 99 pounds. Whoops, LBS. Okay, now the backside then, we're going to talk about, so we're going to do work, which has to do with multiplying the force times the vector. So if F is a constant force whose direction is the same direction as AB, then the work, W done by F and moving the object, would be the product of these two guys. And this is the magnitude of the vector times the magnitude of the force. If it's not, then we use cosine, which all of ours here we can do without doing the cosine. So find the work done by a 10-pound force that's acting in the 1, 2 direction. So basically it's pushing right and up. So think about it's pushing this way, right one. So it's pushing this way. How much would that work in moving an object from 0, 0 to 0, 3? So it's pushing this way, but only part of that's going to be pushing it to the right. So there's just part of that component pushing this way. Okay, so work is going to equal the force times the vector itself. So first off, the force, that's what we're going to use. On this one, I think it's just going to be easier. I mean, this right here, it says 1, 2, but it's in the direction of 1, 2. So this is the magnitude, this is the direction. This is not the magnitude and direction. So I think that's where it gets confusing for me, at least when I'm looking at this. I got to remember, like, this is a 10-pound force, but it happens to be in that direction. It's going right one up to, right one up to. It's going in that direction. Not that it goes right one up to and stops. Okay, so I need to write that first off. I need to figure out what is that. So if it's a magnitude of 10, but it's in this direction, let's make this a unit vector first off, and then I'll multiply by 10s, because this would be 1 unit, and then multiply by 10, that'd be 10 units, 10 pounds of force. So think of this, the unit vector, if you remember, you're going to take 1 over the magnitude, so 1 over the magnitude of this, which would be 1 squared plus 2 squared, so that'd be 5. And then I would take that times the vector itself. So this right here is a unit vector. Now take it times 10. So if I multiply all those together, that would be the force of this vector, 10 pounds force going in that direction. It's not stopping at 1, 2, but that is, it's going to go through 1, 2 and keep going. Now, so that's just the force itself. So this would be 10 radical 5 in the direction of 1, 2. And that's force, but we see up here that work is force with a vector. You're going to dot that with a vector. So work would equal 10 radical 5 and then 1, 2. And then this one, this vector is from 0 to 3. That is actually the distance. We don't move it that far. So this would be 3, 0. And we say multiply by that, it's actually the dot product. So this guy would be 10 radical 2, and because that's a scalar, and then this is going to result in a scalar. 1 times 3 is 3, plus 2 times 0 is 0, so it's going to be 3 times, so that would be 30 divided by radical 5. Okay, now if you look at this was pounds of force. And then this 3, 0 was feet, because we moved it 3 feet from 0, 0. So if it moved it that many feet with this many pounds, then the answer is going to be foot pounds. So it would be 13.42. Couldn't read my own handwriting. Foot pounds. Foot pounds. So we basically just want to know what was this vector, and then we did a dot product in this direction, and that's how work was done. So the result was a scalar when you're looking for work. Okay, the result's a scalar. When you're doing force, the result's a vector, but when you're doing work, the result's going to be a scalar. Find the work done by a force of 24 newtons acting in the direction 4, 5. Again, this is just the direction. Now it's going to go 24 newtons. It's going to go through that point. It may stop at that point, but it's going to go through that point. So let's make this a unit vector and then multiply by 24. So the force be that unit vector, so it'll be 1 over the square root of, so 4 squared would be 16 plus 25, which is 41. And then we'll multiply by the magnitude. So a unit vector times the magnitude, so that's going to be how far it actually goes. and then I need to multiply that in this direction just to see how far it actually goes. So if I multiply these together, that's the actual vector, you know, how far right, how far up it's going. So 24 radical 41, which if you wanted to do that, you could, but I don't need to do that because eventually I'm going to do a dot product with this direction. So this is the force. This represents the force right here, but then the work is going to be the force times the vector itself, the direction of the vector. So in this one, we can, I guess, we'll call that AB if we're using the formula above. So this force was newtons, and then this, how many meters to this point, 5, 0. So that vector, that's how far it needs to go. Yeah, so if I do it, so it'd be 24 over radical 41, do the dot product, so this would be 20 plus 0, so just 20. So then if I multiply those together, again, put it in the calculator if you want, I got 74.96, and that would be Newton meters, which if you really know your physics, that's actually a joule. So I'll put Newton meters in parentheses, was actually how many joules. I'm not going to be too picky about the units. So anyway, very confusing, very, very, very confusing. It's hard to tell. You know, for me, it doesn't click right. So if you're if you're like me, or if you're more like a physics person, maybe that does all click real easy for you. So anyway, hopefully that helps. Just again, kind of try to follow that model, and you know, remember when you're doing force, the result is a vector. When you're doing work, the result is a scalar. Okay, so that helps you know if you got a right answer.